Hello, welcome back to our channel. And today we are going to discuss very basic and important circuits of an operational amplifier called as op-amp in short form. And we will talk about first inverting amplifier. And then we will talk about non-inverting amplifier. Now you might say or wonder, there are so many tutorials available on inverting and non-inverting operational amplifiers. Then what's new in this video? In this video, we will add to the existing knowledge by analyzing and simulating the two circuits response, that is op-amp as an inverting and a non-inverting amplifier. And duration of this video, in the duration of this video, we will also discuss some important parameters that we would come across. For example, changing the op-amp open loop gain and its bandwidth, and see its effect on the output voltage response of the operational amplifier. So before I tell you how to simulate the circuits using inverting and non-inverting amplifier, let me draw the basic schematic that represents the two circuits. So first we will talk about the inverting case. That has, we know that the operational amplifier has positive and the negative inputs. Then it has output terminal. So this is an operational amplifier. It has a gain OAL. AOL is actually an open loop gain of an amplifier. So what you do here, you basically apply an external input signal, that is V in, at some frequency to this inverting terminal through a resistor called as R1, let's say. And then here you have an output, and from the output you apply negative feedback. You feed some portion of the output back to the negative input of the amplifier called as feedback resistor RF. At the same time, you prefer to ground this positive input. So here you have ground also. So with this configuration, your circuit is ready. And now we want to derive an expression of an output voltage. So for an amplifier, we know that the output is given as gain times V in. So our objective is to find out the gain of an amplifier, which is the ratio of output voltage divided by input voltage. So what we will do, we will apply some basic circuit theory to analyze this circuit, and here it is. So we know that your amplifier output, this one, your amplifier input is here, that is going to throw this current I, okay, and this current is flowing through the resistor R1, and now you have this current is there is a current flowing from the output back to the input. So you also have this current, let's say IF. Okay, so at this node, we know that there are two terminals of the op-amp. Here you call it V1, and here you call it V2. Okay, and we will now just apply a law here. So you write an expression such as your input current I would be given as V in minus V1 divided by R1. That is your value of your current I, actually, not I1. This is I, which is this current. Okay. And you say that your output current, your feedback current VO minus V1 would divided by RF is actually equal to IF. And we know that I at this node V1, your I and IF are coming together as a incoming current. So I plus IF will be equal to 0. That is the KCL, applying the KCL here. That is Kirchhoff current law. So we know that we have V1 is at the potential V2, because if the gain of the amplifier is very high, if the AOL very high, then V in is tends to be 0, which is V in is nothing but the voltage difference between the two voltages at the op-amp terminal, V2 minus V1. So you can also write here A equal to V out divided by VID, which is VO divided by V2 minus V1. Okay, or it can also be written as VO divided by V1 minus V2. So if the gain is very high, that means the difference between the two inputs tends to be 0. That is how the beauty of op-amp. So it means if V1 is equal to V2, that means V1 is equal to 0, because V2 is at 0. See, the V2 we have grounded it here. So we can come back to these values of the I1 and IF, or I and IF. So we'll plug in those values in this equation right here. So what we'll write, V in minus 0, because V1 is now 0, divided by R1 plus here the IF value, VO minus 0 divided by RF is equal to 0. So finally, we see that V in divided by R1 is equal to VO divided by RF, right? And now you can write the expression here. This is actually minus, because this term will be uh, coming right here. Okay, so we say that VO divided by V in is equal to minus RF over R1, or we can say that the magnitude, if we take, is equal to RF over R1. So the gain is set by the ratio of the two resistors, and the output voltage is negative of the input. So that's why we call it as an inverting amplifier. It means you have a sine wave applied at the input, you have sine wave output at the output with an amplification factor set by the ratio of the resistors. However, there is a phase shift of 180 degree. Now, having explained this theory in a systematic way, we'll try to build this circuit and we'll simulate the impact of the open loop gain on the output voltage. So we'll have the very high gain given by the given operational amplifier, and we'll expect that we have a wonderful expression such as VO by V in is equal to RF by R1, and we'll have sine wave in the input, sine wave at the output in a very good manner. However, if this condition holds true when we are assuming the V1 is equal to V2, right? But what if the gain is finite, gain is lower? If we can have the operational amplifier with not sufficient gain, in that case V1 is approximately equal to V2. It's not going to be exactly equal to V2. So we'll see how the circuit behaves in that case. So how to do that? So it's very simple. On your screen you see the schematic. I will just click here. Let me take you to this click new schematic, and here you are, and I have explained you the theory behind first. So we'll first click component. Now you see from the library we are going to choose this universal operational amplifier, Why this model? Because it is a linear single pole op-amp with no internal nodes or output voltage range limit. So your output voltage can swing between any limits. And this is the macro model that helps us to set our own gain bandwidth product. In previous video, please refer to that. We have explained about op-amps macro model and the gain bandwidth product, offset voltage, etc. So we'll click OK, and this model is right over here. Then after that, we need to pick up the resistor. So we'll say yes, the resistors have come, and we'll say, okay, 1 watt inverting amplifier. So shift R or control R. So here it goes, then control R, and second resistor goes here. And let's say, then I need a ground terminal. So I will place it here. Then I will place it somewhere here. Then I need a voltage source, which will act as an input voltage. So I will say voltage. That's correct. I need this input voltage source, and I would need one to provide a power supply to the op-amp terminal right here and right here. So that's my power supply. So I will call it like, say, power, because that's giving me a rel. And with that said, but now you see your circuit is not simulating as expected. So we'll do one thing. We'll just drag the schematic away from our theoretical explanation. And maybe we'll zoom in a little bit about, yeah, this is how it is happening. But if we just take this, maybe, then it's much better. So yeah, now we can do that. Now with that data, I will connect the components through the wire. So here it goes. I am connecting them together. Okay, and there is one more ground here that I need, that I will do it. And in a moment, we'll see our circuit is complete. Now I want to label the net here. So I'll right click here, I'll label here, and I'll say that V plus, because that's my positive supply rel. And I will click here, and then I will also click this net here, V plus, because I gave the supply, positive supply to the op-amp. How about I now just select this out, and right here, let me just try to see if I can zoom in. I can just select this portion, and I am able to zoom in, but I can also go there like this. Oh, it's a little bit here and there, but eventually we'll get there. But I have explained you the theory, so no problem. So now what we are going to do is connect the other components. Let's say R1 is here, and then right here, and then I will connect the negative terminal of the op-amp, and I will get back to you when I complete this circuit. As you can see, we have built this circuit almost as it looks. Now it's time to plug in the values. So let's say, let's call it RF. This resistor is RF because that's what we did in our theory. And let's call this resistor R1 because see the schematic in the theory. And the values of RF, let's say we set the gain of 10. So it's, let's say, 10K actually, 10K. And here we'll set the value of 1K. And then we have a DC voltage of, let's say, 1 volt. We'll see we should expect the output voltage will be 10 times the input voltage. So you should have the output voltage to be 10. So for that, I would just connect the net here, and I will call it, right click here, label the net as V out, and I will say it is my output port. So it is how it goes. So let's call it as V out, connect it, and that's it. Now it's time to simulate the circuit doing our first analysis. But before that, let's power our operation amplifier. So here I right click, the name of the power source is power, and I'm putting the DC value of, let's say, 12 volt. And that's it. Once that is done, now I want to do the operating point analysis. So I will like to label this net here. This is my V1. Let's say I'm calling it small v1, and that's the net I have. And then this net, I want to call it as, let's say, V2. That is how I have done that, right? So that's my V2. If I highlight this net, for example, right click this V1, and I see that this is the net. Now I want to do it for the V2. I highlight that, but the V2 is now V2 is ground. We know that in the theory also. Right here we call it as V2. So let's not label it, because we know that it is at the ground potential, right? So just take the scissor and cut it. That's it. Now with that done, we'll click simulate here, edit simulation command, and we'll choose the dot operating point analysis, DC operating point. So it will create the syntax of dot op, place it here. And with that done, now you are set to run the analysis. So come back here, right here, and click simulation, and done. And now let us analyze one by one how your circuit looks like. So how do you do that? So I think I need to clear the drawing now, because I have done the analysis. So clear all drawing. Now you see that. So the voltage at V1 is about 10 micron, 10 microvolts. So at this node, so it is close to zero, but it's not exactly zero, because that's the gain that this macro model of op-amp has. I'll show you in a moment that gain. Then output voltage is minus 10 volt. So which is as expected. I applied 1 volt. Gain was minus RF by R1. So I get minus 10 volt. Correct. This is the voltage source of the power supply, for that is 12 volt. Then at node 001 right here, I have a voltage of 1 volt, which is correct. The current through the RF is about 1 milliamp. The current through R1 is about, again, 0.9 milliamp. So both currents are there, and total current from the drawn from the op-amp power supplies about minus 2.4 into 10 to the power minus 8, so 24 nanoampere. So you see, now I want to show you by right clicking this macro model what gain I have set here. So it is by default, the circuit simulator is giving me the gain of 1 mega, gain bandwidth product of 10 mega, offset voltage of 0, and input impedance about 500 mega. So let us see an impact of changing these parameters one by one on the circuit performance. So right now we have a gain, but voltage at the V1 was about 10 microvolt, as we've seen that at this node. So what if I change the gain to be, let's say, 1 mega? So it is 0.1 mega maybe. I'm just playing with the gain, and we'll see how much the change comes there. Now you can evidently see the voltage at the V1 is no longer close to zero, which is at the positive input. So the impact of reducing the gain, having low gain, open loop gain of an op-amp causes there the difference between V1 and V2 to go increase, because if the gain drops, the difference is going to be larger. Okay, and that causes your output also is not exactly 10, rather it is close to 10, minus 9.9 and something like that. And other things will also, such as currents and all, will change. What if we have significant reduction of in the gain? For example, it is 100K now, but I want to just keep it, let's say 1000. With that, you will see a huge difference between, because the output voltage is your 9, the voltage at the node V1 right here is 9 millivolt. So differential voltage is your 9 millivolt here, actually. The actual voltage difference that comes at the negative and the positive input. And because of that, you have output voltage about minus 9.8. So output is dropping. All right. So the exact what we did, we derived the expression for an approximate uh, gain of an amplifier, but simulating this performance is giving us the exact expression. So you can also derive an exact expression for the operation amplifier output. So that's why it is desirable to have a large gain, as large gain as possible. So I'll go back and set it to 1 mega as before. So let's say 1 e to the power 6, and that's it. How about I now want to change? So you see its output voltage is 10 volt, and your difference voltage between negative and positive voltage, which should ideally be 0, but it is now about 10 micro something. But if I can increase the gain, maybe let's say gain is 10 mega, and we'll see the difference input is about 1 micron. So it's just one order less than the previous value. So it's making sense. How about now I change some other parameter? For example, I change the differential amplifier, this input impedance. So it is like 5 mega, or it was from 500 mega to just say 5K. We'll see. We'll see what happens. Now you see this is also, you have 2.2 microvolt. Output voltage is minus 22. So your operation amplifier as an inverting amplifier doesn't really work, right? So because you have large currents flowing inside the op-amp terminal, the current is 2 milliampere through RF, through R1, but your sub-circuit currents will be different there. So it's like the circuit is not working as expected. So right now we'll just go back, and it was 500 mega. We'll keep it like this. Ideally it should be infinite, as because that allows the having a large differential input impedance allows negligible current to enter inside the op-amp terminals. Okay, so the current comes from here, and that goes through RF like this. Okay, so from the source, and no current can enter inside the negative terminal ideally. Similarly, that's for the positive terminal. Now we'll see what happens here. All right, so you see now the sub-circuit currents inside the op-amp terminal, they are like in the nanoampere range. Earlier it was amperes, and here output is minus 10. Differential voltage is 1 micron. come back to simulate, edit simulation command, and now we'll go for DC sweep. So here name of the first source, that is V1. Then type of this sweep, let's say linear, start value, let's say 0, and stop value, let's say 10, and increment of 1. So all the way gain should be about 10, because that's the ratio of resistors R1, ratio of resistor RF and R1. So now let's simulate. So we got this. So let's click on the schematic that is right here. We see that the input voltage is stepping from 0 to 10 volt at the step of 1 volt, and the output is here. Now you see the output is negative of the input as expected. So when the input is 0, output is 0. Is that clear? The green is the input and the blue is the output. So when the input is 0, output is 0. When the input is 1 volt, the output is minus 10. When the input is 2 volt, the output is minus 20. When the input is 3 volt, the output is minus 30. And when the input is, let's say, 8 volt, here, the output is minus 80. And when the input is 10, the output is minus 100. So perfectly, it is adjusting its output voltage. Let's say we have like effect of gain as previously, it's not 10 mega, rather it is, let's say, 10 to the power 2, just 100. So click OK and run and see how the output is behaving. Well, the output is still catching up, but let's click the voltage at the node V1, how it goes. The voltage at the node 1, so we'll just it should be 0 ideally, right? So I will add plot pane, and the voltage at the V1 is increasing as you increase the input voltage. Your output is also catching up, but your voltage, which is the differential voltage V1 with respect to ground, is increasing from 0 to 100 millivolts with the gain reducing. How about I right click here, and now I go to previous value, that is 10 to the power 6, and then I simulate, and now you see it is stepping from 0 approximately to, it was 1 micron, something like that, and now it is catching up to only 11 microvolts. So you see that the differential voltage, because op-amp essentially is an amplifier that amplifies the difference between the two inputs, right? So this is the situation here. So, okay, so now we have understood this analysis very well. It's time now to do some time domain analysis. So for that, what I'll do, I'll right click. Let's say I click advanced and then I choose pulse. So I have to provide initial value, let's say 0, then turn V on, voltage is say 1 volt. Delay is about 10 nanosecond. Rise time is about 10 nanosecond. Fall time is about 10 nanosecond. T on time is like say 1 millisecond. Period is about 1 millisecond. Then the T on will be 0.5 milliseconds. And I don't specify the cycles, or maybe 10 cycles. I apply this signal and this syntax comes here. Now I want to run the transient. So simulate, edit simulation command. I will choose transient here, and then stop time, let's say 10 milli, and start saving data from 0. Maximum state I don't specify, or maybe let's say 1 milli. And this is the syntax right here. Click OK. Click place it here. As soon as I place it here, other two analyses are disabled. Click simulation. And now we see we don't need to analyze now V1. So just delete this pane. And now you can see your input and output relationship. So just add plot pane, say V1 is up. It is from 0 to 1 volt at the frequency of 1 kilohertz, and the output is -10. So out of phase signals, inverting amplifier is correctly drawn. So when your input is 1 volt, output is -10. When your input is 0 again, the output is 0. And the situation continues like that. So that's how you do this one. How about running the frequency response? Try to, now I will show you how to plot the body response. Body response is a plot that gives you gain versus frequency and phase versus frequency. So you can express your gain magnitude or take the decibels, dB values of it. So we'll do that. So click simulate. Before that, we just place, will not select the pulse now. For the AC analysis, we'll click none. Then we'll go here, AC amplitude is set to 1. And then that's it. We'll just click OK. So here you have your AC, small signal AC source. And now you don't want to run all these analyses. Rather, you click simulate, edit simulation command, then click AC analysis, choose the type of sweep. So it is going to compute you small signal AC behavior of the circuit linearized about its DC operating point. So choose decade, number of points per decade, let's say 1000 points. Start frequency is about, let's say 1. Stop frequency is about, let's say 10 mega, right? So see, the syntax is ready here. .ac dec 1001 10 to the power 6. Click OK. As soon as you place it here, the other analyses are disabled. Save, simulate. And here you have, we don't need to the green one, so we'll just click and delete this pane. Now I see the blue one. I have a gain of 20 dB. So remember the gain of this circuit. Let me write it for you. It is V out divided by V in. The magnitude is 10. So in dB, it would be given as 20 log of V out divided by V in. So it would be 20 log 10, and that is 20 log 0 is 0 dB. 20 log 1 is 0 dB. 20 log 10 is 20 dB. I think so. Yeah, I think so. So that's how. But if I right click here, I will show you right now. Let me just click here. That is, just right click the axis and I will choose linear. Yeah. So you see the gain is 10. 9.9 exactly. So let me choose the different color for the phase. So why not just maybe, can we choose the color for the phase? The dotted one is the phase, the faint one, and the dark one, solid line, is your gain. So 9.9 from 0, from 1 hertz, from low frequency. So it is a low pass filter. Now you have the identify where it is a single pole op-amp. I have explained you indicated that in the beginning. So here you have 200 kilohertz. This is 300, 400 something, and we got to find the -3 dB point. So I will right click here. Let's say right click and click decibel. Click OK, and here I have the -3 dB point where I have my first pole. So let's figure that out. So here is 20 dB minus 3 dB will be about 17 dB right here. So it is in this case somewhere here. It's about 1 mega. Yeah, it's about 1 mega minus 3 dB point at 1 megahertz. So this is how I have this frequency response of this. And the phase is, as you can see, at low frequency, the phase is about 180 degree, and then it's dropped to minus 160, no, 180 degree, and then it drops to plus 160 degree. And then afterwards it goes to lowest value about 88 degree, and the gain also goes to 0 dB. So you basically, your operating region of this op-amp, your operating region of this op-amp is this region. This region, this is your operating region. So that's a very good way to understand the behavior. Now I show you a little change. I don't want, let's say, the gain bandwidth product. I explained that in a previous video, refer to that. This is the gain bandwidth product about 10 meg. So what if I want to just reduce it to one order, maybe 0.1 meg or 0.01 meg. So we'll see what difference it makes. Click. And now you see suddenly your gain bandwidth product is less. It means you have the single pole. Your gain is still 20 dB, but your bandwidth is decreased now. Your bandwidth is dropped. Your bandwidth is somewhere here, is about 10 kilohertz, right? So that's the effect of having a low gain bandwidth product. So because you actually decreased your frequency for a constant gain. So gain bandwidth is what about changing the gain, keeping the gain bandwidth product constant? For example, we have, let's say, we have gain bandwidth product is about 10 meg as before, 10 mega. That's fine, but and then I simulate and it is just like before. You have a minus 3 dB point at 1 mega for a gain of 20 dB. What if I increase the gain? If I increase the gain, your bandwidth should decrease to keep the gain bandwidth product constant. So let's keep it, let's say 100K. So it's now the gain is up, and that's expected. Your gain is up. Now it is 40 dB. You can see your gain is 40 dB, but your minus 3 dB point is somewhere here. So it's about 80 kilohertz is your minus 3 dB point. So from 1 mega, you came to 80 kilohertz. So it's a huge difference. So that's how when you design the op-amp, you have to trade between the gain and the bandwidth. So hope you like this video. You found it informative. If so, click the like button, comment on the videos what you would like to see further and what topics you would like to explore, and we'll try to bring it to you. And do share with others for a wider reach. And till then, wish you happy learning. Don't forget to subscribe the channel.